yourself that it's anything, right? Yeah, and then, other possible answers. That's okay. Somebody, another take on that answer? Or different one? Yeah. Right, the forward rate. Right, and it's not necessarily variable. I mean, it's just that it depends on the substrate. Other takes on it? All right. So yeah. So this is interesting. I'm gonna argue that the most reasonable way to view this would give you, as long as there is some finite concentration of that substrate around, then I think that there's a very well-defined sense in which it's going to go some finite fraction. Okay. And I think that when you're thinking about this in the context of kind of molecular kinetics, kind of like the chemistry view, I mean, it still is all well-defined, but the way that I think that I get the most clear intuition is just to imagine myself as being that one and only enzyme in the test tube. Okay? Now, there's going to be some rate that I bind to the substrate, right? And that's going to be, and what's going to determine that rate in this kind of, yeah, the concentration of the substrate, right? So if I double the substrate concentration, what should that do to the rate of me binding? Double it, yeah, right? And then, of course, there's always this kf somewhere in there in some units, right? But there's going to be some rate that I bind, right? And then when I bind, again, now I'm just an enzyme substrate. Now, instead of thinking about this in the context of kind of chemical kinetics, I can just think about this from the standpoint of an individual molecule where I'm a complex, E and S bound, and there's some rate that I fall apart, right? And it's just the balance of those two rates of kind of binding a substrate and then falling apart that's going to lead to this this fraction bound. Okay. Yeah. Yeah. Yes. Yeah. So right. So I mean, if you'd like, we could put an average on it. To say an average over time. Yeah. Because in many cases, what we're really interested in is the fraction of the time that say the promoter is bound or the enzyme is bound or whatnot. And if you have many molecules, then at any moment in time, the average is kind of time average. But once you get to a single molecule, then you really want to get time. We're gonna we'll revisit this in just a moment. Using the math. But what's interesting is the math also can mislead you. So you have to. Are there other questions? I'm happy to take, if somebody wants to argue forcefully that what their neighbor said was right, then I'm happy to. Right. Yeah, we will come back to this in a little bit. All right, so I want to do the fourth possibility, which is the concentration, total concentration of the enzyme. It's going to go to infinity, and yeah, so I'll just give you, again, 8 seconds to think and then get your card. All right, are you ready? All right, 3, 2, 1. Okay, so we actually have a fair amount of different between A's and B's, it seems. I think there are enough. All right, so go ahead and, yeah, again, turn to your neighbor, but, maybe find somebody that disagrees with you. There are, sometimes there are pockets of people that agree one way or the other, so, or that think one, so, try to find each other. Yeah. There are lots of open problems. I don't mean to indicate everything's known. This is I should double check that it's definitely not known, but pretty sure it's open. Because of this rotation issue, there's kind of a lot of things to worry about. So it's not clear how efficiently you can encode a solution. Maybe you need a ton of bits of precision to say how things are rotated. Here they're all rotated at the same angle. They may not be. Who knows? Check that it's definitely not known, but pretty sure it's open. Because of this rotation issue, there's kind of a lot of things to worry about. So it's not clear how efficiently you can encode a solution. Maybe you need a ton of bits of precision to say how things are rotated. Here they're all rotated at the same angle. They may not be. Who knows? So we will consider a special case, which is exact packing. This also makes for a stronger with a let's start with a reduction from partition. Partition is a synonym for two partition. Usually we omit the two. So reduction from partition, this problem over here. So now I'm given some integers. I want to split them in half, basically. Any suggestions on what I could do to turn that into a multi-processor scheduling problem? Two processors, yep. P equals 2. That is the reduction. I guess technically I also have to specify what T is, but it's over there. So you set T to be the sum of the A's over 2, and you don't change A, you just leave it alone. So you just feed in the same AIs into this problem, and that is 2 partition. Okay, let's do a reduction from, so now we know the problem is at least weakly NP-hard, but in fact it is strongly NP-hard, because we can reduce from 3 partition. What do? P equals N over 3. That's it. You set T accordingly, so the A is over T. Done. Okay, this problem comes from the paper that introduces 3 partition, which is by Gary and Johnson, same people who wrote the book. So this basically is 3 partition. That's why they cared about it, but here's a practical motivation for it.
Cool. Let's do something more interesting. And I'm going to want a projector.